Thanks for coming. I'm Dean Wampler. I also work at IBM. Actually, I did report to Anthony, who did the keynote this morning. Carl and I did, and we might report to him again. You never know how things go at IBM. But this talk is kind of a result of some things I learned doing that experience of working with Anthony on science projects. If you haven't been to any of my talks, I just put photos of my travels or whatever, and these photos are from the Blue Ridge Parkway about a month ago in Virginia, including pulling onto the parkway, and there was like a 60s vintage car ahead of me on the road, so a little bit of a throwback maybe.
Did you make it while moving?
Well, I'm sitting here with my phone. If you look carefully, you'll notice there's actually reflections from the dashboard in the picture. You can just barely see, there's like streak of brightness right here. But anyway, enough about the process. All right, let's talk about science. So I actually started as a scientist. I did nuclear physics, and it was all theoretical stuff, which sounds more impressive than it actually was. I was mostly writing simulations for nuclear and particle processes. Basically doing kind of, well, not really big data so much, but just lots of number crunching, the sort of stuff we do today. When I did it back in the late 80s, we had these things called mini-vax computers. If anyone have any idea what I'm talking about? All right, some of you, yeah, those of you that have gray hair too. I would start these simulations running, come back 2 weeks later and see if they were done. And that's why grad school takes so long, basically. But anyway, that's kind of good. Actually, I've discovered I really liked writing software. So in fact, when I finished my doctorate, I got into software as a profession. And so I've kind of been in both worlds a little bit and kind of can appreciate the needs and interests and motivations for both sides as well. And so recently, I led the engineering team for this group that Anthony was running for accelerated discovery, meaning like using software to accelerate basically chemistry. And trying to productize some of the software that was developed in actually our Zurich lab at IBM. And learned a lot of interesting things about it and enjoyed getting back into science just a little bit. So I've had this fabulous life of science and software. Before I go over the topics, how many of you would call yourself a scientist? Oh, cool. How many of you think of yourselves more as just a regular software engineer? Probably most of you. And how many of you are sort of in the middle? You're actually a software engineer, but writing for science. Okay. Okay, cool. Great. So here's what I thought I would talk about. First, what does open mean? Because kind of the topic here is, is there an important idea here that we can steal from software about open source software, apply it to science, and what does that mean? And how does that make things better for all of us? What are the different motivations each of these groups have? And then how can they learn lessons from each other? And I had a definition in when you see OSS, it's open source software, and then I don't know who it was that research came up with, I guess it was Alexi, OSSCI for open source science. All right, so what does it mean? This is kind of an interesting topic because it means different things to different people. So I took this definition, and it's not even the complete definition, but a list of key attributes from this open source initiative, and I'll tell you in a minute where that came from. But part of the idea is free redistribution, that if I wrote something and made it open source, then you could use it and run it yourself. It doesn't necessarily mean source, actually, and a great example right now are models. Like if you use the Llama generative AI model from Meta, you're mostly getting data that represents the model weights and then some code that's actually run at runtime. So we're kind of, although we tend to have thought about open source as being source code, in fact, it could be a lot of different things, and including data, as we'll get into a little bit. This was an interesting definition too, because they get into a lot about it should be non-discriminatory. It should be open to anybody to use, any institution, any people, non-discriminatory in the good sense. But we'll also talk about ways in which maybe you don't want to be open in that sense in just a second. One of the big areas where licenses for openness differ is what do you do, how is something licensed that is derived from your work? And one of the controversial areas, at least in software, has been that some of the original proponents of openness, namely like the Free Software Foundation, out of MIT really wanted to say that if you take our software and use it, you have to make the source code for everything you build open as well, which doesn't really fly very well in a lot of enterprise environments. Whereas other organizations are more flexible and they use licensing that says you can do what you want with it as long as you, attribute your, the code that you're using to us, but use it as you see fit. And then usually there's a lot of details about how the license propagates with the code, so you can't like change the license of someone else's software and so forth. So let's talk about a few of the complications though about this. And by the way, I know that some of this is kind of like old hat for some of you, and hopefully it'll still be useful, but I'm trying to talk about things that are maybe not so well known to scientists and also things that maybe are not so well known to software people. All right, so one of the big issues has been commercial versus non-commercial use, and one of the big areas that's controversial right now is actually Llama, where at least for Llama version 1, you were not allowed to use it for commercial purposes. You could use it for research. They actually loosened that license for Llama version 2. Again, this is the model from Meta. But other organizations have gone the other direction, and it's been very controversial. Like, Confluent changed the license for Kafka. Elasticsearch changed their license. I know some of you have worked with Scala a lot, and Lightbend and the company behind Scala originally, and Akka, and they decided to change the license for Akka to make it, to actually require you to have a license if you're going to use it for commercial applications. And companies do this even though it makes everyone mad because they want to make money off stuff that maybe other people are using for free and they're not getting any benefit from. So it's kind of a difficult part of the open source as a business model. Now I mentioned that already that source code has kind of been the way we've thought about software and openness for a long time, but really data is almost more important today in some contexts like AI, where the model is almost like the crown jewel and not so much the code used around the model or even how you trained it. And then this idea of non-discrimination is great in principle, but some of you may recall that the Java license specifically prohibited you from using Java to run nuclear power plants. So similarly, you might decide that you want it to be only used for good, like no weapons or whatever you define good to be, but hopefully not in any sort of like discrimination against various groups of people. So again, complications. And if we keep going here, I mentioned that some of the licenses have been considered toxic because they impose restrictions on you that may be unacceptable, like the GNU General License, GNU Public License, GPL actually, really required you to release your source code if you use their stuff. And that sort of is true for Linux, which is based on a lot of GPL stuff, but other systems, they've come up with different variants of that license to kind of address the complaints. But it has been a real headache for people to decide what software can I use based on what license it supports. And generally the rule of thumb in enterprises is avoid GPL stuff, with some exceptions like Linux, but Apache and MIT and Berkeley licenses are considered really easy to deal with and good. Okay, anyway. However you define openness, a little history is kind of interesting, and this is something I just found out this week as I was researching this from this Wikipedia article, that one of the first examples of sharing, in a sense, was actually automobile patents. There was apparently a patent that was very restrictive on two-cylinder engines that was controlled by monopoly at the turn of the 20th century. Somehow Henry Ford won a lawsuit against the patent holder, and the outcome of it was they formed an automobile association where they would freely share all their patents. They would actually continue patenting stuff, but they would just share it with all the manufacturers. So they kind of decided it was actually better to work in collaborative ways like this than try to enforce patents. IBM has actually apparently made the source code for their operating systems and a lot of their tools basically available for people to use. And there's this old organization called SHARE, which is not an acronym, and another organization called GUIDE, which is an acronym, where people would take code from IBM, modify it, tweak it to do things they needed to do in mainframes, and this community has existed now since the 50s. BSD was probably the first famous Linux variant that was open source in a sense, in our modern sense of the word, and of course eventually Linux followed that model. The actual term, though, wasn't the first term that was used. Free software was the term that was used by the people behind the GNU public license. But the actual term open source was believed to have been coined by a lady, I forget what her actual job was, Christine Peterson. This was some time ago. And then there was like a slew of things that started down this path of openness, like Netscape Navigator famously made their code open for the first real commercial web browser. Eric Raymond and some other people created that open source initiative and became evangelists for open source. And then O'Reilly, the publisher, and the company, and Tim O'Reilly, the founder, became real advocates and started the first open source summits. There's actually one that's run by the Linux Foundation today because O'Reilly no longer does conferences. Okay, anyway, so that's sort of a history of this idea that maybe it's actually better if we work together in the open on things where we can mutually benefit from each other sharing rather than try to keep everything proprietary. So what are the motivations then for people to actually want to do this, to want to embrace openness? Well, for software engineers, and this of course I'm preaching to the choir here, one of the big goals is to actually collaborate with peers to get common needs done. Well, one of the ways I like to frame this when I'm talking to people about whether, like, say, IBM should open source something or not is, what's our core competency? What's our crown jewels? What is the thing that differentiates us from making money versus things that we need but aren't necessarily going to make us money or not? It would be better for us to collaborate with other people, is one way I kind of like to frame that question. And why do we collaborate? Well, again, we can save effort, we can get the best ideas out there, work together. Open source often has the best quality of software compared to proprietary software. It also helps people learn ideas as they kind of steal each other's good ideas from various open source projects. Actually, one of my colleagues is a substitute speaker this afternoon. Nick Hill's going to talk about optimizations for inference with language models. And there's like this real sort of fervency going on as people have various open source and limited source projects for inference, and they keep inventing new ways to optimize performance of something that's extremely expensive, which is running stuff on GPUs. And so everybody's kind of stealing each other's ideas, if you will. And actually, there's also this whole social thing. People loved the recognition of, hey, I helped build that project, or I'm a committer on that project. I really like working with colleagues that share similar interests and skills and all that stuff. So it sort of meets that social need a bit. So also, when software engineers want to evaluate a project they're going to use, possibly, is they really care about. They'll give you 10 or 15 minutes, right? If they see your repo has claims to do something they need, they want to be able to clone that open source repo very quickly, figure out what it does, build it if building's required, install it, maybe run some examples. They want to know within a few minutes if this really works, just right out of the box, and then start to explore if it's really right for them. And so if any one of those things doesn't work for some reason, or it's unusually difficult to do something with this software, then it's going to be much harder for people to adopt it. So, and part of that then has instilled this notion that you really have to think about the end user, the client, if you will, of your software, if it's going to be good and if it's going to get traction in the industry. Whereas sometimes you don't think about the kind of low-level client or user or accessibility when you're working on proprietary stuff. You may only care about the user interface that your end users are going to see. And then lastly, for software engineers, as a result, then we really expect high quality and reliability and all ease of use and all these sort of abilities that are really important for us, because we don't want to waste our time because we're always really stressed with deadlines, right? Well, the motivations of scientists are a little different, but they're also similar in a lot of ways. Like typically, they want to collaborate with colleagues. I mean, the joke, of course, is that scientists and software engineers are real introverts. And if you meet a scientist or a software engineer, the way you can tell if they're actually an extrovert as opposed to an introvert is, do they look at your shoes instead of their own shoes, right? But in fact, people do like to collaborate and share ideas and get the best of both worlds going for them, so they're not kind of on their own and kind of bored or whatever. But one of the interesting things that's really a main priority that has driven openness in science in the last few years is the need for reproducibility of results. You know, if you've done some serious simulation of, let's say, climate, or I saw a really cool one recently of simulating the collision of whatever body hit the Earth to create the moon. People want to be able to reproduce that to verify that it's, you know, good science and so forth. So that's kind of driven this idea that maybe we should make everything data as well as code public so people can try it out and verify for themselves whether it works. Now I put in an asterisk here. When I say scientist, I'm just sort of the umbrella of a team that could be software people as well as actual, you know, scientists with doctorates or whatever. But one thing that scientists traditionally have not been all that worried about is kind of this idea that the software they're writing is going to become part of some, you know, shrink wrap in the old days, or a, you know, a cloud service today. What we use this kind of not very great term, production, for that sort of software that has to be delivered, reliable, makes money for somebody, or, you know, provides critical functionality. Usually it's a much less formal process in research software historically than that kind of sort of bar, if you will, of quality that production software people have to meet. The thing that has been very interesting for me, I'll come back to this a little bit later also, is that historically, probably data has been as important as the actual code in science. You know, whether it's your lab data or whatever you use to feed into simulations, that has often been just as important as any sort of code that you use to do this. Whereas that really has not been true in software. As I said, open source, the very word actually implies that it's really about source code, but increasingly today, especially in this AI world with models, data can be just as important. And I keep saying models, but also what data was used to train those models. So there's a lot of work about, should we open source the data sets that we use to train them? All right. So what can you know, scientists, people who want to embrace openness in the science realm, learn from open source software? Well, it turns out, I heard an interesting talk, actually I guess it was this spring at Go2 Chicago, which is, you know, a general developer conference like this one, by a guy who'd spent some time talking to people in other industries about, you know, their pain points, what do they do? I mean, people like architects, you know, construction people, what were some of the others? I think he talked to some printers. And one of the things he kind of found out is that nobody does like reproducible processes quite as good as we do. It is actually a strength. Now, we don't necessarily always do it like we should or to the extent we should, but in terms of like having processes that can reproducibly recreate something that we have built in the past, you know, like give me version 5 because I need to patch it for this customer over here or whatever, we're actually pretty good at that. And those are techniques that are not the first thing that come to mind when you're writing science software per se, where you might just be doing a lot of experimenting, trying out ideas, and hoping that you come on to something that's useful. But the interesting analog, though, I think in science is actually like the lab notebook, which today is typically, you know, online with Jupyter or something. But the reason you do notebooks historically in science was so that you could, you know, go back and look at what happened. How did I get to this point? Why did that experiment seem to go better than the ones I've done since, and so forth? So it's your memory of what seemed to work and what didn't. And similarly, we have these techniques in software that we similarly use for reproducibility. And some of those techniques include what I just called asset management. This is where you store your code or maybe your data, or the build tools you use, your documentation, whatever, and version it as you're evolving it. And the tool of choice now is Git. It's absolutely taken over the world in terms of this process in software. But it also provides ways of not only tracking your work, but sharing it with others. You know, if I have a public Git repo in GitHub, then I can, you know, share it with colleagues either in the office or across the country that, you know, are in entirely different industries or whatever, and we can all work collaboratively on it, or they can just use it if they want. And I think, did I put that in here? Anyway, the other point being also that we can, branch and release in the notes on the right, that I can work in parallel on some ideas while other people are working on stuff. I can merge these things in a very controlled way so I know I didn't break anything. And then when I release something and say, yeah, let's go ahead and ship this to production or whatever, I know exactly what's in it. I can come back later and reproduce it if I have to fix bugs or whatever. So it's a really mature process these days, and although you do find that a lot of people don't use it as much as you would think. And it's definitely like the first thing I would tell a science organization is start using these version tracking tools and get in this habit of just saving everything, including Jupyter notebooks or whatever, because you'll really learn not only to think constructively and sort of rigorously about how your work is proceeding, but you can then go back and revisit things that you've already moved past on. The other thing that we've gotten a lot better on, just in my career, it's actually, this is one of the maybe most significant ways we've improved, is ways of verifying the behavior of something. When I started, back in the Pleistocene writing software, the way you tested stuff was you installed it and you poked around and hoped that it worked, and then you did another build later, and hopefully you followed the same procedures you did, but you probably didn't follow them exactly, so any bugs you introduced likely went unnoticed. But now we've figured out how to write very rigorous ways of defining behavior and verifying that our software actually meets that behavior. And this is another thing where if you're working in science, you have this same idea too. If you have a theorem, let's say, you want to verify that it actually works. And you want to be your own worst critic, right? You don't want someone to tell you that your research is garbage and you have to retract your paper from Nature or something like that. You really want to be your own worst critic. And this is the kind of thing that we all really find that we have to do together, is figure out what's the best way to verify behavior so that we're really confident that what we think is going on really is going on. Does the software actually do what we think it's supposed to do? And does this experiment actually prove the theory that I think it does, that kind of stuff. But in software, we've quickly learned, and I think this is becoming more and more true in science as well, is that process of testing, no matter how good your tests are, if they're manual, it becomes extremely painful to do them. Also, if there's a non-trivial build and installation process, not only is it very tedious and time-consuming, but there's just plenty of opportunity for human error if you're doing them manually. So automation becomes extremely essential. And to the point where really mature software environments basically automate everything. So as soon as the developer commits to a branch, some code changes, pushes that branch up to this common repo, then automation kicks in to run all the tests, to do some integration things that are hard to do on your laptop, let's say, to really build confidence that this software is still good, that nothing has broken by these changes. And similarly in science, I remember some of the software I wrote in college or grad school was like these big Fortran programs. This is long before I knew anything about test-driven development, but it was really tough for me to know that I hadn't broken something because I didn't know anything about testing at the time or automation. But now, I think that's really, these are like power tools. Even if you don't think you need them so much in science, they are such powerful tools that they make you a lot more productive in the long run, especially for long-running projects. Like I know, for example, that some of the data analysis tools at like CERN, some of these simulations for climate, these are massive, massive programs. They are decades old. I don't know much about how they're developed, but I would not want to be working on those things if they're sort of just ad hoc and there's no real processes involved in keeping these things sane, automated, tested, and so forth. The other thing that's, to me, always an interesting topic is what language ecosystem am I going to use? And I use the term ecosystem, well, it's not just me, but the term that not only means the language, but like the libraries and so forth. One of the talks I was in this morning mentioned that you can find a library for anything in Python, which is now kind of our de facto choice in science for like the high-level analysis stuff. Even if you're running Fortran libraries that are 5 decades old underneath, which you probably are, languages that are easy to use, easy to learn, let you think about your problem and not how to capture it in code, but also give you the tools you need to do your work. Those are pretty important decisions. One of the things for me about languages, I've always been interested in them. we seem to go through cycles of experimentation. Like I remember when I first really got interested in software in the 80s, it was the era of object-oriented programming, which some of you may remember. And there were just all these object-oriented languages floating around. There was like something called C++. There was Smalltalk, which sadly kind of died off. But people were experimenting with ideas and how to represent these concepts of objects in ways that let them work efficiently. And then we kind of consolidated into languages like C and C++. We had another flurry of languages in the functional programming era a few years ago. Well, more like 10 or 15 years ago. You know, Clojure, F# for Amanda back there. Languages like that really got people thinking in new ways about how to structure software and to think logically about it. And then we kind of consolidated into a few. And that's where we are right now, I think, is we're all doing either Python, maybe Rust, maybe Go. But already from our keynote discussion this morning, we're starting to see new languages emerge that try to tackle the problems of our existing languages, like Mojo. So that's exciting to me. Okay, to wrap up fairly quickly here, I'm almost out of time, but one other thing that's really important that goes with reproducibility and all that is really thinking about the dependencies of libraries you pull in. One of the problems we ran into a lot at IBM Research was people would just slapdash throw stuff in their projects because some little library over here did this thing they needed. And you'd even get situations where they actually had they had sort of pulled in several versions of the same library in their whole system, which were incompatible in some sense. So thinking about managing these versions is really crucial to keep things sane for you and for the people that have to work with your software, like the ones who are checking it out to maybe use. And a related thing is keep those dependencies up to date because vulnerabilities are identified. You know, these are like security vulnerabilities all the time. And if you keep your versions up to date, then you'll avoid some common problems. All right, quickly, what can the software world learn from science? Well, one is this idea that data is actually really important, and we need to actually figure out better ways to manage data. Like GitHub is not actually a great way to manage data. It doesn't really like big things. Like it complains about the size of my presentations a lot if they get over like 50 megabytes. So we need better ways to manage and catalog data that fits more of our model of working iteratively and quickly, not just throwing stuff in databases where maybe it's not versioned as well as we'd like. And this is becoming just extremely important because of models and data sets for models in AI. The science world has been doing distributed computing a lot longer than most of us have in software. You know, they invented supercomputers. They invented, high-performance computing. And this is stuff that we've kind of reinvented a number of times to figure out how to do this stuff ourselves. And in some ways, we've built things that maybe fit our needs better in software than highly optimized hardware. And yet, here we are in the AI world where everyone is trying to throw money at NVIDIA for massive GPU clusters because we just need massive amounts of compute. So I think learning what science has done with scaled out distributed computing can help us think more clearly about how we should approach this problem in software. All right, so just to wrap up, just make sure I got this right. For science, I think that increasingly, as always in the entire world that we live in, software gets more and more important and it becomes part of the research you're delivering so people can reproduce your results, and it's a way of you collaborating with your peers on non-trivial projects. So think about embracing these, this should be embrace open source software, forget that bullet point, and kind of leverage those techniques. Oh, I know what I meant by this, sorry. Think about not just keeping stuff closed, but actually opening it up. Is it better for you to share your work at that level rather than just publish papers about it? Because then you can collaborate more easily and people can verify that your work's good. And then for software, I think we don't know how to handle probabilistic and statistical stuff. And that's something that the science community has dealt with forever, even apart from like quantum computing. So this is something that we have to get better at. But also being better at distributed computing is something that all of us in software just can no longer avoid, even though we hide it under abstractions like Kubernetes and so forth. Okay, well, I'll wrap up there since I'm out of time. And I guess I'll just take questions in the room. Thanks.